Welcome to today's Explainer. Today, we're shining a spotlight on a crucial yet completely invisible world inside every single HVAC system, and that's refrigeration oils. Understanding the exact chemistry of these lubricants, it's literally the difference between a system humming along for 20 years and one that absolutely destroys itself in a matter of months.
Okay, let's dive into a catastrophic field failure to really set the stakes here. This quote comes from a real-world scenario encountered by Jumperman Tech. A multi-$1,000 LG compressor died not once, but twice in just 7 months. I mean, the inverter board completely melted one of the legs, the power board went bad, it was just a total, unbelievable meltdown. And the culprit? It wasn't just a faulty part. It was actually a chain reaction of systemic failures that basically turned the system's own oil right against it.
So here's our game plan for today. We'll start with the anatomy of that exact failure, then cover the essential rules of oil chemistry. After that, we'll compare the different types of refrigeration oils you'll see in the field, look at how to perfectly match oil to refrigerants, and finally, we'll cover diagnostics and some crucial EPA rules.
All right, Section 1, the anatomy of a failure, and what happens when systems just completely collapse.
So in the case of that failing LG system we just mentioned, it really wasn't just bad luck. The system had incredibly low pressure and these completely packed dirty indoor coils that hadn't been cleaned in like 12 years. That severe lack of airflow meant the refrigerant simply wasn't boiling off into a vapor like it's supposed to. Instead, liquid refrigerant migrated right back to the compressor. And remember, compressors are vapor pumps, right? They absolutely can't pump liquid. To make matters even worse, hollowed-out filter dryer casings were just left in the suction line, and they acted like giant traps, swallowing up all the oil. The compressor essentially starved to death from a lack of lubrication while choking on liquid. It's a nightmare scenario.
Moving on to Section 2, Essential Oil Chemistry Basics. Let's look at the invisible rules governing these systems.
First up, we've got miscibility. Now, refrigeration oil doesn't just pump itself. It has to ride along with the refrigerant vapor as this sort of entrained mist. Miscibility is simply the ability of that oil to effectively mix with the refrigerant at various temperatures. If the oil and refrigerant separate too much, especially in a cold evaporator, well, the oil just gets stranded there and never actually makes it back to the compressor.
Next up is hygroscopy. This is the tendency of an oil to attract and hold on to moisture right out of the air. It acts exactly like a chemical sponge. Now, older oils were relatively forgiving with this, but many of the modern synthetic oils we use today, they are highly hygroscopic. So if you just leave a container uncapped while you're working, or you fail to pull a really deep vacuum, you are directly introducing moisture into the lifeblood of that system.
And that moisture leads us directly to our most dangerous term, hydrolysis. This is a chemical decomposition caused by a reaction with water. So the really crucial takeaway here is that when certain synthetic oils absorb water, they literally break down into harmful acids and alcohol. And guys, once hydrolysis occurs, it is a one-way street. You absolutely cannot reverse this chemical reaction by throwing on line dryers or just pulling a deeper vacuum. That acid is going to eat the system from the inside out.
Take a look at this illustration of a typical heat pump. It brilliantly shows how oil is discharged from the compressor right along with the hot gas. Now, an oil separator will catch a lot of it, sure, but some oil inevitably travels all the way through the condenser, the expansion valve, and into the evaporator. From there, it relies entirely on the velocity of the refrigerant and good miscibility to make that uphill journey back to the compressor via the suction line.
Okay, Section 3. Let's compare the actual types of refrigeration oils. Let's look at the roster.
We'll kick things off with the traditional oils, mineral oil and alkylbenzene. Mineral oil is your classic refined petroleum product. It's stable, it's low cost, and frankly, it forgives a whole lot of sloppy field practices. But, and it's a big but, it is exclusively used for older CFC and HCFC refrigerants, like R22. It absolutely will not mix with modern HFC or HFO refrigerants. Then you have alkylbenzene, or AB, which is a synthetic that blends perfectly with mineral oil. We often see it used to improve miscibility in heavy-duty commercial HCFC systems operating at really low temperatures.
But as we phased out those ozone-depleting refrigerants, we had to invent totally new lubricants. Enter the ultimate synthetic showdown. POE versus PAG.
Now, what is super interesting about this comparison is the hidden electrical difference between these two. POE, or polyester, is highly miscible with modern refrigerants, but unfortunately, it suffers from that dreaded hydrolysis we talked about earlier. However, POE is a fantastic electrical insulator.
PAG, on the other hand, polyalkylene glycol, is incredibly stable and can actually lock in moisture without ever forming sludge. But get this, PAG is highly electrically conductive. So if you accidentally put PAG oil into a hybrid or electric vehicle compressor that specifically requires PoE, the conductivity of that PAG oil will literally short out the high-voltage compressor.
So next, we have the modern alternatives, PVE and PAO. PVE, or polyvinyl ether, is fascinating stuff. It's highly hygroscopic, meaning, yes, it absorbs water super easily, but it does not undergo hydrolysis. No way, right? That means it won't form those nasty acids. And unlike PoE, PVE can actually be dehydrated again just by using your vacuum pump. That's why it's incredibly popular in VRF and ductless systems. PAO, on the other hand, is basically the heavyweight champion for natural refrigerants like ammonia. It has supreme thermal stability, which is perfect for preventing those horrible carbon coke deposits from forming at really high discharge temperatures.
Let's jump into Section 4, matching oil to refrigerants and the compatibility risks involved.
This compatibility matrix right here, consider this your survival guide. If you're running CFCs or HFCSs, you stick strictly to mineral oil, alkyl benzene, or PoE. If you're working with modern HFCs or HFOs, you must use synthetics like PoE, PVE, or PAG. You just cannot use mineral oil with HFCs. They will immediately separate. And for those ammonia systems, PAO is your preferred go-to. Mixing incompatible oils and refrigerants is a recipe for disaster. It results in liquid separation, completely stripping the compressor of its lubrication.
And this concept becomes absolutely critical during retrofits. When you're converting an older R22 system over to a modern HFO or HFC blend, you have to remove the old mineral oil. Because it won't mix with the new refrigerant, any residual mineral oil is just going to coat the inside of the evaporator tubes, totally destroying your heat transfer. So you have to use successive PoE oil flushes to dilute that residual mineral oil down to 5% or less just to maintain proper mass flow and cooling capacity.
But we have to remember, even if your chemical miscibility is 100% perfect, you can still suffer from something called oil logging. Say your cooling load drops, maybe it's just mild weather and you have a variable speed compressor running, your refrigerant mass flow just plummets. If that refrigerant vapor velocity drops below the critical threshold, which is about 700 feet per minute, well, gravity wins. The oil falls right out of the vapor and just pools in the coils, quietly robbing your compressor of its lifeblood until it completely seizes up.
Finally, Section 5, diagnostics and EPA rules out in the field. Connecting back to that crazy opening story, detecting hydrolysis early is absolutely critical. You can use simple tools like the new Calgon Quick Check 2-second test right on the low-side suction line while the system is still running. If that vapor turns the paper pink, bad news, you have inorganic acids eating your system. You can also do a physical oil bottle test. If the chemical mixture keeps a nice bright purple color, you're good to go. Your acid numbers are at safe passing levels.
Okay, so you pull that bad oil out, now you have to manage it legally. The EPA has a very specific three-pronged definition of used oil. First, it has to originate from crude or synthetic materials. Second, it must have actually been used as a lubricant or heat transfer fluid. And third, it must be contaminated by physical or chemical impurities during that actual use. Interestingly enough, if you happen to spill virgin oil before it ever goes into a machine, it actually does not legally count as used oil under this specific RCRA definition. Kind of a wild loophole, right?
When it comes to compliance, the rules are really grounded in just basic, strict housekeeping. All containers have to be clearly labeled as used oil. And guys, never ever mix used oil with solvents or hazardous waste. Doing that triggers a massive, incredibly costly hazardous waste nightmare. As for oil filters, you've got to puncture them, hot drain them, and completely crush them before you can recycle them as scrap metal.
So I want to leave you with this final thought to ponder today. Considering just how incredibly sensitive modern PoE and PAG oils are to moisture and electrical conductivity, is your daily handling of these lubricants secretly setting up your next catastrophic compressor failure? Respect the chemistry, pull a really deep vacuum, match your oils perfectly, and I promise you, your systems are going to thrive. Thanks so much for joining me on this explainer, and as always, keep learning.